In last session, we learnt about Euclid's division algorithm. Now we will understand the fundamental theorem of arithmetic. We are covering both of these concepts first and then we will solve questions related to these topics. Because many of questions can be solved by both of these concepts. Means there will be two ways to solve a single question. Let's understand this theorem. We have taken prime factorization of 4620 using tree method. We can take prime factorization in another way also. In fact, there are many versions of this prime factorization. I am trying to say that we can take any prime number first to initiate this tree method. Now you can see all of these three prime factors are same. The only difference is order by which they are arranged. Now they are same. Note that all these factors are prime and you already know about prime numbers. In this case, all of these are prime numbers. And what is special about these numbers? They are factors, or we can say divisors are only one and itself. And all of these are composite numbers. And what is their speciality? They have always more than two factors, means they have more than two divisors. If someone asks you what is the definition of prime numbers, then what will you say? A positive integer p is prime if p is not equal to 1 and the positive divisors of p are 1 and p itself. Note that here it is said that p is not equal to 1, means 1 is not a prime number. But why? If someone asks you why 1 is not a prime number, then what will you say? You can pause and think about it. Okay, if you don't know, we will find it soon. But for now, just tell me the definition of fundamental theorem of arithmetic. The process we seen right now is called the fundamental theorem of arithmetic. Let's write it down. Every composite number can be expressed as a product of prime numbers. And also this factorization is unique except the order by which prime factors are represented. What does it mean? We just saw that the prime factorization of 4620 can be represented in three different ways. In fact, we can write it in hundreds of forms. But when we arrange these prime factors in ascending or descending order, then we find that all of these are equal to each other. This is the fact that we have been told in the theorem. Means if we avoid the order of this prime factorization, this will be unique. It was all about fundamental theorem of arithmetic. Now let's understand why 1 is not considered as a prime number. 2 can be factorized as 1 and 2. 11 can also be written as 1 into 11. But what about 1? We can also factorize 1 as 1 into 1 because 1 into 1 is 1. Now let's assume 1 is also a prime number and we just understood the prime factorization of 4620 is unique. Means no other factors will look like this ever. As we saw that we wrote the prime factorization of 4620 in three different forms and all of these three factors were same. Now if we assume 1 as a prime number, then we can include it in these prime factors. We can also multiply 1 3 times in this factorization. Any number multiplied by 1 gives the same number. We don't get any change in that number. In fact, we can multiply 1 infinite times. Now we just understood the uniqueness of prime factorization. But now it is not unique. We can write it in many forms and they will be different from each other. Means now 4620 have many prime factorizations. To avoid this mathematical error, our mathematicians removed 1 from the group of prime numbers. That's why 2 is called the smallest prime number and also 2 is only the even prime number. Means all other prime numbers except 2 are always odd. If you notice, you will find a problem, and what that problem is, tell me which concept came into existence first, fundamental theorem of arithmetic or definition of prime numbers. Because according to fundamental theorem of arithmetic, 1 is not a prime number because it breaks the rule of uniqueness of prime factorization. Means we removed 1 from the group of prime numbers on the basis of fundamental theorem of arithmetic. On the other hand, we can say the definition of prime numbers was invented first. Means we did not consider 1 as a prime number from the beginning of the concept of the prime number. Means we already considered that 1 is not a prime number. And then on the basis of prime numbers, we defined fundamental theorem of arithmetic. In mathematics, every concept and theory is derived from other concept or theory. Means we already know that this concept came first and then we created another theory with the help of this first concept. Means this is a two-sided thing. We cannot say that which came first, egg or hen. Now this conflict is up to you. Solve this puzzle by yourself. That was all about fundamental theorem of arithmetic. Let's understand some more concepts and theories. It is saying that p is a prime number, so we have taken some prime numbers. And it is also saying that a is a positive integer, so we have taken some positive integers. Now it is said in the theorem that if p divides a square, then p divides a. So we will take the squares of these positive integers, means all of them are a square. Notice that 2 divides 4 and also 2 divides 2. Means p divides a square and p also divides a. Again 3 divides 9, means p divides a square, and 3 also divides 3, means p divides a. Also 11 divides 121 and it also divides 11, means if p divides a square, then p also divides a. You can see there is a line between p and a. It is the symbol of division. Okay, we understood this theorem. What is the use of this theorem? So we will use this theorem to prove these questions. Means to prove the irrationality of irrational numbers, we use this theorem when we prove root 2 is irrational. If you notice, you will find that p is prime, and also we have taken a as positive integer, and the number whose square has been divided by p is also prime, means a is also a prime number. If p divides a square, then it is clear that a is also p, means prime. It was all about this theorem. Some students may say to prove this theorem, because any law can be applicable on 2 or 3 numbers, but it is not necessary that it would be applicable on every positive integer. That's why we take variables to prove any theorem, because variables are universal numbers, means we can take any number in place of these variables. So should we prove this theorem? The answer is no, because no one will ask you about proving this theorem, and there is no chance to ask this theorem in examination, so there is no need to prove it. But if you still want to prove it, you can comment, we will prove this theorem also. We learned many important topics till now, but still we have some points to learn. Let's see. There is a very interesting relation between HCF and LCM. Let's see it. If we have given two numbers a and b, we will multiply the HCF and LCM of a and b, and the product we get will be equal to the product of these two numbers a and b. Let's understand it. We have taken the prime factorization of 24 and 32. Let's assume 24 is a and 32 is b. Here 2 is multiplied 3 times, means we can write 2 to the power 3 into 3. Also 2 is 5 times in the prime factorization of 32, means it is 2 power 3 into 2 power 2. Now 2 power 3 is common in all these two factors, means HCF will be 8. Let's find out the LCM of 24 and 32. 3 can be written as 3 to the power 1 and it can be written as 2 power 5. So how do we find LCM? First of all, we find how many numbers are there in both factors. In this case, there is 2 and 3 only. Now we will take the numbers which have greatest powers. Means if we look at 2 power 3 and 2 power 5, 2 to the power 5 is greater than 2 to the power 3. So we will take it. And we also have another number 3. So we will look for its greatest power. Here 3 is given only one time. Means whatever will be its power, that will be its highest power. So we will take it and multiply it by 2 to the power 5. Now we have 2 to the power 5, means 2 is multiplied 5 times and 3 is multiplied 1 time. Their product will be 96, means LCM is 96. LCM means least common multiple. You can also understand LCM in another way. Here we have taken the tables of 24 and 32. You can see 96 is common in both multiples. Also 192 and 288 are common. But 96 is smaller than all other common multiples. That's why 96 is called least common multiple. Now let's see what we get after multiplying HCF and LCM. So HCF is 8 and LCM is 96. By multiplying them, we get 768. Now we will multiply first and second number, and this time we will also get 768. Means the product of HCF and LCM of a and b is also equal to the product of a and b. But what if we take another number? That means third number. As we have taken 60 here, so now would this relation be true or false for these three numbers? Let's see what we get. HCF of these three numbers will be 4, because now 2 to the power 2 is only common in these three factors. Now what will be their LCM? Again we will see how many numbers are there in these factors. We already had 2 and 3. Now 5 is also included, means their LCM is 2 to the power 5 into 3 into 5, which is 480. By multiplying HCF and LCM, we get 1920. And by multiplying these three numbers together, we get 46,080. you can see they are not equal. Means this rule is not applicable on 3 or more numbers. Let's bring HCF and LCM of 24 and 32 back. Now if someone asks you relation between HCF and LCM, you can tell it easily. But what if someone asks you to prove it? Because he does not believe in the given statement, so you will give him some examples so that he will be satisfied. But if he is not convinced by your few examples, because a theorem can be applicable on 2 or 4 examples, but it is not necessarily true that it would work on all possible numbers. So would you show him many examples to prove your point? I think it is not the right way to prove it. There is no need to do this. We will prove this law once, and the person asking the question will also be satisfied. The proof of the relation between HCF and LCM is not given in secondary school books. It is also not given in ISC. You will have to learn BSc to prove this theorem, because you will find the solution of this theorem in graduation. And you can also see its proof is looking too much complicated and long. But don't worry, we will prove this theorem in a simple and easy way. Let's see how. Let's assume A and B are two positive integers, and HCF is H and LCM is L. Let's assume 24 is A and 32 is B. Their HCF is 8 and LCM is 96. Now we are going to do something which is the key point to prove this theorem. Means if you understand this step, you can prove this theorem easily. We will take 24 and divide it by 8. Means we have divided 24 by HCF 8 and we get 3. Be careful, it is the 3 which we got in these prime factors. Means if we send 8 on other side, we will get 2 to the power 3 into 3. But we don't have to do so. Now 24 is A and 8 is H. Let's assume this 3 is x. Don't think too much, just take 3 as x. Now we get A by H equal to x. Again we will take 32 and divide it by HCF means 8. This time we will get 4. Notice that 8 can be written as 2 into 2 into 2 and 4 can be written as 2 into 2. Means if we send 8 on other side, we will get 8 into 4, which we have already written above. Don't think about it. Now look at our theorem. Notice we have considered 32 as B and 8 as H, means HCF. Now let's assume 4B Y. Now we will put H on other side and get A is equal to X into H and B is equal to Y into H. It's an obvious thing, you can do it easily. Now let's find A into B. That means first number into second number. We will put X into H in place of A and Y into H in place of B. Now we get X into Y into H square because H is 2 times. Let's assume it first equation. Notice now we have found the product of first and second number. That means A into B. Now if we find HCF into LCM is equal to X into Y into H square somehow, then we proved our theorem. Let's find out LCM. We know HCF is H. But what is LCM? Here we have taken LCM. Notice that 2 into 2 into 2 is 8, which can be written as H, means HCF. In the same way, we can write 2 into 2 as Y, because we just considered 4 as Y, and 2 into 2 is 4. Now tell me what is 3? 3 can be written as X, because we just considered 3 as X, means LCM is X into Y into H. Now you can see, we have proved our theorem, because we found LCM, and if we multiply it by HCF means H, we get X into Y into H square. And remember, we just considered X into Y into H square as equation first. You can also see it here. You can also say, I don't get that logic. I can't understand it. How it can be possible to prove this theorem in such a way? So don't worry. We will take another way to understand it. Means we will find LCM using another way. Here we have taken 5 and 6 in place of A and B. Now let's find the LCM of 5 and 6. We can take any number in place of A and B. So don't be confused. It is just for understanding. So we have taken the table of 5 and also we have taken the table of 6. Now 30 and 60 are common in both multiples. 3 is the smallest, so it is the LCM. You can notice we have simply multiplied 5 by 6 because we cannot take anything common from 5 and 6, and hence we got 30, which is LCM. But what happens if we take 10 in place of 5 and 12 in place of 6? Now what will be the LCM of 10 and 12? So 10 can be written as 5 into 2 and 12 is 6 into 2. Notice H is beneath 2, means 2 is common in both 10 and 12 and H is common in both A and B. Now LCM of 10 and 12 will be 5 into 6 into 2, which is 60. Means we have taken 2 only one time to find the LCM. In the same way, when we take the LCM of A and B, then we will take H only one time. Means we will get X into Y into H as LCM. Please again don't tell me that you still didn't recognize this process. Anyone can understand this phenomena. So we get LCM as x into y into h. And the region is A is x into h and B is y into h. We already considered HCF as h. Now let's multiply HCF and LCM. We will put h in place of HCF and we will put x into y into h in place of LCM. Here h is 2 times, so we can write it as x into y into h square. Let's say it equation second. You can see now first and second equations are equal to each other. That means we proved product of HCF and LCM is equal to the product of first and second number. It is enough for today. In next session, we will solve questions based on these theorems. See you soon.